Up until now, whenever we've done any of our algebra using a Cartesian grid, we've had points or vectors that only have an x and a y component. If we look at this point here, it looks like it has an x component of 3 and a y component of 1. So this looks like the point 3, 1. But what we're going to do now, since our world is in 3 dimensions, we're going to learn how to plot points and draw vectors and do algebra with vectors in 3 dimensions. So what do I mean by working in 3 dimensions? Well, let's watch as I manipulate this graph in the GeoGebra app. Notice there's actually a third axis, a z-axis, and that point has a z component along with its x and y component. It has a z component of 3 as well. So we're going to learn in this lesson how we can plot points and draw vectors in 3 dimensions. So this lesson is lesson 4, Vectors in 3 Space, from the grade 12 Calculus and Vectors course, and it's the 5th unit Cartesian vectors. So like I said, in this lesson we're going to learn how to do algebra with vectors in 3 dimensions. So we have this z-axis added to our x and y axis, and it's perpendicular to the xy plane. So each of our vectors is going to have 3 components. We're adding this third z component to our vectors so that we can work with vectors in 3 dimensions. So we're going to take everything we've learned about vectors in 2 dimensions and learn how to apply that to vectors in 3 dimensions. So when you're ready to get started, head on over to jensenmath.ca. Once you're here, go to the grade 12 Calculus and Vectors course. Find the 5th unit, the 2nd vectors unit, Cartesian vectors, and we're doing lesson 4, Vectors in 3 Space. So once on this page, you can get a blank copy of the lesson here. You can get a blank copy of the practice questions here, and then when you're done your practice questions, you can check your solutions by clicking on Worksheet Solutions. So, let's get started. So at the beginning of this lesson, we're going to learn how to start by drawing the x, y, and z axes on our page. So it's kind of difficult to represent 3 dimensions on a 2-dimensional page, but we do our best, and we're going to follow some general guidelines so that we all have the same general orientations of our axes, because there's an infinite number of ways we could draw the x, y, and axes on our page, so we're all going to follow the same general pattern. So the main thing we have to agree on after we've drawn our x, y, and z axes is in which direction is the positive x, positive y, and positive z axis. And we'll use the right-hand rule, which is demonstrated with this diagram right here. So it says here there are several ways to choose the orientation of the positive axes, but we'll use what is called the right-hand system. If we imagine ourselves looking down the positive z-axis, so we choose the positive z-axis as this axis right here. If we imagine ourselves looking down that positive z-axis, when the positive x-axis is rotated 90 degrees counterclockwise, so this way, it becomes coincident with the positive y-axis. That's called the right-hand rule. And another way of phrasing that, look here, if you curl your fingers of your right hand from the positive x-axis to the positive y-axis, your thumb will point along the positive z-axis. So let's look back in GeoGebra just to make sure you get a good visual of that. So here in GeoGebra again, how can we tell where the positive x, y, and z axes are? If we look down the positive z-axis, so if we choose this to be the positive z-axis, if we were to look straight down on that positive z-axis, if we were to move this x-axis 90 degrees counterclockwise, it would become coincident with the positive y-axis. That means that this is positive x, and this is positive y. It wouldn't be positive y over here because that would be moving it clockwise 90 degrees. Positive y must be over here because if we move the positive x counterclockwise 90 degrees, it would be coincident with that axis. So before we draw vectors in 3 space, let's make sure we could plot some points in 3 space. So this point, 2, negative 3, 7, has an x, a y, and a z component. If we're to plot that point, we start by moving 2 units along the positive x-axis. So that brings us to right here. That's represented by that arrow. And then from there, the y component of negative 3 tells us to move 3 units parallel to the negative y-axis. So that's represented by this direction. So now we're here. And then we have to move 7 units parallel to the positive z-axis because of the positive 7 z-coordinate. So that would be represented with that direction right there. And that brings us to our final place, the point itself. 0.2, negative 3, 7. So to get to that point, we went 2 along the positive x-axis, 3 parallel to the negative y-axis, and then 7 parallel to the positive z-axis. So let's try plotting some points on our own. So I've drawn the grid for us. If this is our positive z-axis, and this is the positive x-axis, this would have to be positive y, because if I rotated this one 90 degrees counterclockwise, it would be coincident with that axis. So that's the right-hand system. So when I plot the point 2, 6, 1, I have to move 2 units along the positive x-axis. I would then have to move 6 units parallel to the positive y-axis. So I need to move that far along the positive y-axis from where I am after I've moved 2 along the positive x-axis. So this line is 6 units parallel to the positive y-axis. And then I would have to move 1 unit parallel to the positive z-axis. So I would have to move that far along the positive z-axis from where I am after moving in the x and y direction. So that brings me to a point right about here. So that is the point 2, 6, 1. If I get rid of these directional arrows that got me there, hopefully you can imagine that point being in 3 dimensions. And let me show you in GeoGebra how what we got actually makes sense once we are able to rotate these axes and actually visualize it in 3 dimensions. So here's that point 2, 6, 1. It looks just like what we got. As I rotate, you can see that we moved 2 along the positive x, we moved 6 parallel to positive y, and 1 parallel to the positive z. And that brings us to that point. And as we rotate, we can see that that point is now in 3 dimensions. Let's try another one. This point, point 0, 0, 6. So once again, this point has an x, a y, and a z component. So I need to move 0 in the x direction and 0 in the y direction, and 6 in the z direction. So that's easy. All I have to do is move along the z-axis 6 units, and there's my point. Let's try a third one. Point 2, 3, 0, x, y, and z components. So I need to move 2 along the positive x-axis, and then 3 parallel to the positive y-axis. And now I need to do that from where I got to after moving along the x-axis. So that brings me to this point right here. And I'll show you that in GeoGebra as well. So here it is. Here's the point 2, 3, 0. Notice there is no z component. It lies exactly in the xy plane. We haven't moved along the z-axis at all. So there it is rotating. You can visualize it in 3 dimensions. All right, this is the last point we'll practice plotting before we get into work with vectors. So this point has an x, a y, and a z component. So the x component of -1 means move 1 unit in the direction of the negative x-axis. So along the negative x-axis, I will move 1 unit. And then -3 is a y component, means move 3 units parallel to the negative y-axis. So 3 units along the negative y-axis would be that length in that direction. So do that exact movement from where I got to after moving 1 unit along the negative x-axis. And now I need to move 4 units along the positive z-axis. And now I need to move 4 units parallel to the positive z-axis. So that would look like this. So do that movement from where I am after moving along the negative x and negative y axis. And that brings me to my final point right here. So here's point D. X component of -1, y component of -3, z component of 4. And there's the point D. Let's visualize that one in GeoGebra as well. And here we go. Here's that point, -1, -3, 4. And I'll rotate it so you can see it in 3 dimensions. Now that we know how to plot points in 3 dimensions, let's see if we can draw vectors in 3 dimensions. So in this diagram here, I have in positive x-axis, positive y-axis, positive z-axis, and I have a vector v. And when we have algebraic vectors in component form, we know that the tail is at the origin, and the tip is at whatever point is represented by these x, y, and z components that we see inside of square brackets. So if this point right here is point x, y, z, then we would define this vector v as vector x, y, z in square brackets. So let me just let you visualize a vector in 3 dimensions quickly. So let me just make up a random vector. Let's say vector 5, 2, -2. So there's the vector. Let me move around a little bit so you can see that this vector is in 3 dimensions, and this is what it looks like. So vector 5, 2, negative 2 has its tail at the origin, and it has the tip at the point. Let me plot the point. And its tip at that point, 5, 2, negative 2. 5 along the positive x, 2 parallel to the positive y-axis, and then 2 parallel to the negative z-axis. And it brings us that vector right there. So just like in 2 dimensions, we could express a vector as the sum of multiples of unit vectors, we can do the same. So remember, we call the unit vector, and I should mention, a unit vector is a vector with magnitude of 1. So the unit vector parallel to the x-axis, we call unit vector I. The unit vector parallel to the y-axis, we call unit vector j. And since we now have a z-axis, we need a third unit vector. We'll call that unit vector k. And when we have unit vectors, typically the symbol is a hat above the vector, indicating that it is the unit vector, so magnitude of 1. So unit vector I would be the vector 1, 0, 0. That would tell you just to go 1 unit along the x-axis. Unit vector j is the vector 0, 1, 0. That means only go 1 unit along the positive y-axis. And unit vector k is the unit vector 0, 0, 1. That means only go 1 unit along the positive z. So it's commonly understood, if you see unit vector I, j, or k, that's what we're talking about. So this just shows you that we can write any vector as a sum of multiples of unit vectors I, j, and k. So this point right here, point ABC, if that's where the tip of the vector is, we can create the vector that starts at the origin and finishes at that point by adding multiples of the unit vectors. So whatever the x component of this point is, in this case we'll call it a, this vector right here would be equal to a times unit vector I. And whatever the y component of the point is, we'll call it b. This vector along the y-axis would be equal to that y component b times unit vector j. And whatever the z component is, we'll call it c. This vector along the z-axis would be equal to c times unit vector k. So in drawing the vector, to get from where we start at the origin to where the vector finishes at that point ABC, we could just add the 3 vectors, a times unit vector I, plus b times unit vector j, plus c times unit vector k, and by add them I mean place them tip to tail, and that brings us from the beginning to the end of the vector. So you can see that unit vector v is equal to a times I plus b times j plus c times k. And then that's all this is representing to you here. Let me demonstrate this to you in GeoGebra as well. So on this graph, I have this vector still, 5, 2, negative 2, that I made up. Starts at the origin, finishes at the point 5, 2, negative 2. I also have the unit vectors I, j, and k. I could represent this vector, which I've called vector m, as a sum of multiples of these unit vectors. So I just take the x component, multiply that by unit vector I, and it looks like this. Take the y component, multiply it by unit vector j, it looks like this. And take the z component, multiply it by unit vector k, and it looks like this. And then if I add these vectors together, so place them tip to tail, it will equal this vector m. So let me show you that. So there we go. Do you see once they're placed tip to tail, we start at the origin and we finish at point m. So 5 times vector I plus 2 times vector j minus 2 times vector k gets us vector m. So this is just a way of me demonstrating to you that we can represent a vector as sums of multiples of the unit vectors I, j, and k. Let's now learn about some formulas we can use with vectors in 3 dimensions so that we can actually doing some examples where we work with vectors in 3 dimensions. So this vector, vector u, starts at the origin and finishes at the point P, which has x component A, y component B, z component C. So this would be vector A, B, C, written like that in component form. How do we find the magnitude of this vector? Well, all we have to do is apply what we know about Pythagorean theorem. But first of all, to get to this point, we would go A units along the positive x-axis, right? So I could label this side A units. The magnitude of that side is equal to A. And then I would move B units parallel to the y-axis. So the length of this side is equal to whatever the y component is, B. And then I would move C units parallel to the z-axis. So this side right here, represented by this dotted line, would have a magnitude equal to C. So I should be able to use what I know about Pythagorean theorem to solve for the magnitude of that vector. If we look at this right triangle right here, with the right angle right there, we know that the sum of the squares of the legs would equal the square of the hypotenuse. So the magnitude of vector u squared would equal the magnitude of this side. I'll call that vector OR. So the magnitude of vector OR squared plus the magnitude of this side, which we've said is equal to whatever the z component of the vector is equal to. So plus c squared. And now I need to rewrite the magnitude of that sideline, vector OR. I can do that by looking at this right triangle here with the right angle right there. Notice that the magnitude of vector OR squared would equal a squared plus b squared because of that right triangle. So over here, the magnitude of u squared would equal, well, I can replace this with a squared plus b squared. And then I can isolate the magnitude of u by square rooting both sides, and I get the magnitude of u equals the square root of a squared plus b squared plus c squared. So all I have to do to find the magnitude of a vector in 3 space is do the square root of the sum of the squares of all 3 components. So let's start doing some examples where we'll actually do some work with some vectors in 3 dimensions. So this vector u has 3 components, an x, a y, and a z component. I know this vector would start at the origin and finish at the point 3, negative 1, 2. So if I want to sketch that vector, I need to start by plotting the point 3, negative 1, 2, and then connecting a point from the origin to that point. So to plot the point 3, negative 1, 2, I would have to move 3 units along the positive x-axis. I would then have to move 1 unit parallel to the negative y-axis, and I would then have to move 2 units parallel to the positive z-axis. And that would bring me to the point. So now that I've drawn the point, I can draw the vector that would start at the origin and go to that point. So I can get rid of these directional arrows I used to help me get to that point, and I can now draw the vector that starts at the origin and goes to that point. So there I've drawn vector u. Let me just show you in GeoGebra once again so we get a good 3D visualization of that vector. Once again, here's the vector 3, negative 1, 2, represented by that orange vector, which for some reason I called a in GeoGebra here. Notice 3 along positive x, 1 parallel to negative y, 2 parallel to positive z. And that brings me from the origin to that point, and that's vector u. Part B asks us to express it as a sum of multiples of unit vectors. So remember, vector u is equal to vector 3, negative 1, 2. So I could express that as a sum of multiples of unit vectors I, j, and k simply by doing the x component multiplied by unit vector I plus the y component multiplied by unit vector j. So plus a negative, I could just write that as minus 1 times unit vector j plus the z component times unit vector k, so plus 2 times unit vector k. So that's vector u written as a sum of multiples of unit vectors I, j, and k. Part C asks us to find the magnitude, so we can use our magnitude formula we figured out. The magnitude of vector u would just equal the square root of the sum of the squares of the x, y, and z components. The square root of 3 squared plus negative 1 squared plus 2 squared. And we can simplify this. Magnitude of u would equal the square root of 9 plus 1 is 10 plus 2 is 14. So it's equal to root 14 units. And we'll leave that in exact form. Example 3, it gives me 2 points. Each point is in 3 dimensions. They both have an x, y, and z component. And part A asks us to find the magnitude of vector AB. So I first have to figure out how to write vector AB in component form as an algebraic vector. And when we did that in 2 dimensions, remember we found the x component by doing the difference in the x coordinates of the 2 vectors, and we found the y component by doing the difference in the y components of the 2 vectors. So when working in 3 dimensions, same thing, it's just we have to add the 3rd component by finding the difference in the 2 z components. And whenever we're doing these differences, it's very important that we always do tip minus tail for the component differences. So in this notation, vector AB, the tail is at A, and the tip is at B. So when we're finding the algebraic representation of this vector when its tail is at the origin, we always do the difference in all of the components, but do tip minus tail. So 5 minus 1, 4 minus 3, and negative 2 minus 1. Let me make sure you can visualize what we're given. So I'll show you in GeoGebra. that we're given the vector between points A and B. So I have plotted point A and point B here for you. And we know we have the vector that starts at A and finishes at B. But when I want to write this vector as an algebraic vector, I need to write it as if it was translated so that its tail is at the origin. Right now its tail is over here at A. I need to translate this vector, move this vector, keeping its magnitude and direction, but move its tail so it's at the origin. And I do that by finding the difference in each of the x, y, and z components. So like I said, when we do those differences, when we're writing vector AB as an algebraic vector, make sure you do each of the components of the tip minus each of the components of the tail. Always tip minus tail. So we'll start by finding the x component of vector AB by doing the x component of the tip minus the x component of the tail. So 5 minus 1. I then find the y component of vector AB by doing the y coordinate of the tip minus the y coordinate of the tail, so 4 minus 3. And I find the z component by doing the z coordinate of the tip minus the z coordinate of the tail, so negative 2 minus 1. So vector AB, if I translate it so its tail is at the origin, would be vector 4, 1, negative 3. Let's graph this vector and make sure it looks like it has the same magnitude and direction of the vector that starts at A and finishes at B. Okay, there we go. So I graphed the vector 4, negative 1, 3. Notice those vectors have the exact same magnitude and direction. It's just I've translated it so that its tail is now at the origin. So last reminder, whenever we're doing these differences, always tip minus tail. And we know which one is the tip and tail based on the order of the letters in this representation of the vector. The first letter is the tail, the second letter is the tip. So now we need to find the magnitude of this vector. So the magnitude of vector AB would equal the square root of the sum of the squares of the x, y, and z components. So the square root of 4 squared plus 1 squared plus negative 3 squared. And that's equal to the square root of 16 plus 1 is 17, plus 9 is 26. So it's root 26 units. That's the exact magnitude of vector AB. B says find a unit vector u in the same direction as AB. So I need a vector that is in the exact same direction as vector AB. So here's vector AB translated so its tail is at the origin. I want a vector that goes in the exact same direction, but its magnitude is 1. So I need to multiply this vector, vector AB, by a scalar that reduces its magnitude to 1. How do we do that? We just multiply the vector by 1 over its magnitude. So a unit vector, we'll call that unit vector u, is equal to vector AB multiplied by 1 over its magnitude. So 1 over root 26 times vector AB, which was 4, 1, negative 3. If we do this scalar multiplication, we get a vector that's in the exact same direction as AB, but with a magnitude of 1. So unit vector u equals 4 over root 26, 1 over root 26, negative 3 over root 26. And I suppose we could rationalize each of those components. Multiply top and bottom of each of those fractions by root 26. So I would actually take any of these 3 lines as the correct answer to this question. It's just important to know that to create a unit vector, you just multiply the vector by 1 over its magnitude. And that keeps it going in the same direction as the original vector, but it changes its magnitude to 1. So let me just show you on here that if I were to multiply this vector, vector v, by 1 over root 26, it would change its magnitude to 1. Okay, so notice I graphed a new vector. I called it vector w, which is 1 over root 26 times vector AB. And so it's going in the exact same direction as vector AB was, but its length is now 1. And to prove that to you, I got GeoGebra to calculate the length, and it says the length of that vector is 1. Okay, we are going to finish off this lesson by applying all of these rules about vector addition, subtraction, magnitudes of vectors, dot product, projections even. All of those rules we learned about vectors in 2 dimensions to vectors in 3 dimensions. So we're just going to add a third component to each of them. It follows all the same rules. It's just you're going to notice there is this third component involved in all of them, where we work with the z components of our vectors now that we're working in 3 dimensions. So example 4 asks us to simplify each of the following expressions given vectors u, v, and w, which are vectors in 3 dimensions. So let's do a scalar multiplication of vector v. So if I want to do negative 3 times vector v, I have to do negative 3 times vector 8, negative 4, 3. So all I have to do for this one is multiply the x, y, and z components by negative 3. So I have to do negative 3 times 8, that's negative 24. Negative 3 times negative 4, that's 12. And negative 3 times 3, that's negative 9. So this vector would have 3 times the magnitude of vector v, and it would be going in the opposite direction. That's what doing a scalar multiplication of negative 3 by a vector would do. Now I'm going to do the sum of vectors u, v, and w. So this would equal vector u, which is 2, 3, negative 5, plus vector v, which is 8, negative 4, 3, plus vector w, which is negative 6, negative 2, 0. When adding algebraic vectors, to get the x component, I just have to add the 3 x components of the vectors, 2, 8, and negative 6, and that will give me the x component of the resultant vector. To get the y component of the resultant vector, just add the y component of those 3 vectors, 3, negative 4, and negative 2. And to get the z component, let's just add the z components of those 3 vectors, negative 5, 3, and 0. So my resultant vector would have an x component of 4, a y component of negative 3, and a z component of negative 2. Part C says find the magnitude of u minus v. So let me start by figuring out what vector u minus v is, and then I'll find its magnitude. So vector u is vector 2, 3, negative 5, and I need to subtract vector v, which is vector 8, negative 4, 3. So I have to just subtract the x components. 2 minus 8 is negative 6. Subtract the y components. 3 minus negative 4 is 7. And subtract the z components. Negative 5 minus 3 is negative 8. Now I need to find the magnitude of u minus v. What we have found so far is just u minus v. I now need to find its magnitude by doing the square root of the sum of the squares of all 3 components. So the square root of negative 6 squared plus 7 squared plus negative 8 squared. And that would equal the square root of 149. Let's do a dot product question now. So remember the formula for dot product. If we have algebraic vectors, let's look down here. To find the dot product of u and v, all I have to do is find the product of the x components, and then add the product of the y components, and add the product of the z components. So u dot v, let me start by rewriting I have vector u and v right here, so that's helpful. So if I want u dot v, remember my answer is just going to be a scalar. It's not going to be a vector. I have to multiply the x components of u and v, 2 times 8, plus multiply the y components, 3 and negative 4, plus multiply the z components, negative 5 and 3. And now find these products and sums. 16 minus 12 minus 15. So that will give me negative 11. Example 5 says determine if the vectors a and b are collinear. They're collinear if and only if they are scalar multiples of each other. So they would only be collinear if vector a equals a scalar multiple of vector b. That's the only way they can be collinear. And remember, collinear means they fall on the exact same line. So let me check. Are each of the components, the x components, the y components, and the z components, are they all the same scalar multiples of each other? So I'm going to set myself up 3 equations, one for each of the components. So the x components, they're scalar multiples of each other. So 6 equals k times 9. The y components are scalar multiples of each other. 2 equals some scalar multiplication of 3. And the z components are also scalar multiples of each other. 4 is equal to some scalar multiple of 6. They'll only be collinear if each of these equations has the same solution for k. If the scalar multiplication to get between the x coordinates, y coordinates, and z coordinates are all exactly the same. That's the only way that vector a could be equal to a scalar multiple of vector b. So let's solve each of these equations for k. This one I would get 2/3. This one I would get 2/3. And this one I would also get 2/3. So what I could say is vector a is equal to 2/3 of vector b, since all of these are the exact same k value. Vector a equals 2/3 vector b. If I multiplied this vector by 2/3, right, each of the components would get multiplied by 2/3, and that would give me this vector. That means that the vectors are parallel. They are collinear. They fall on the exact same line. Let me show that to you in GeoGebra. Okay, so here are vector a and b. Notice that they fall on the exact same line. And if I multiply vector b by 2/3, it should become an equivalent vector to vector a. There we go. So Hopefully you can see now that these two vectors are now the same if I multiplied vector b by 2/3. So I've verified that vector a and b are scalar multiples of each other, which means they are collinear. Example 6 asks us to find a value of a such that this vector and this vector are collinear. So they're only collinear if they're scalar multiples of each other. So let me just call this vector u and this vector v. So they would only be collinear if vector u was equal to a scalar multiple of vector v. And they would only be scalar multiples if the x, y, and z components were all the same scalar multiples of each other. So let's look at the x component. 1 equals some scalar multiple of 2. 2 equals some scalar multiple of a. And 3 equals some scalar multiple of 6. And in order for these to be collinear, all of these k values would have to be the same. So let's check what the scalar multiplication is between the x and the z components, and then make sure the y component has that same scalar multiplication. So solve for k in this equation, we get a half. Solve for k in this equation, we get a half. Right, so it's clear all we have to do to get from vector v to vector u is multiply vector v by a half. Multiply this component by a half, we get this component. Multiply this component by half, we get this component. So we're looking here, what can I multiply by a half to get 2? So we've solved that k is a half, so in this equation, change k to a half, and now solve for a. So just multiply the 2 to the other side, a equals 4. So we figured out if a was 4, then vector u would equal a half of vector v. Example 7 says calculate the angle between these two vectors. To find the angle between two algebraic vectors, we just have to use rearranged dot product. And here's a reminder of that rearranged dot product formula. So to find the angle between vector u and v, I would have to do u dot v divided by the magnitude of u times the magnitude of v. So cosine of the angle would equal, let's do the dot product of vector u and v. So that's the sum of the products of the x, y, and z components. So find the product of the x components, 0 and 6, plus the product of the y components, -1 and 1, plus the product of the z components, -4 and -2. And that will give me the dot product of the two vectors. It'll give me a scalar. It'll give me the magnitude of one of the vectors multiplied by the magnitude of the projection of the other vector onto the first vector. I have to divide this by the magnitude of vector u times the magnitude of vector v. So I can find the magnitude of vector u by doing the square root of the sum of the squares of its components. So that will give me the magnitude of vector u. I have to multiply that by the magnitude of vector v, which would be the square root of 6 squared plus 1 squared plus -2 squared. And now I just have to simplify this and do inverse cosine of the ratio, and I'll get the angle. And we'll get the angle in degrees. The numerator simplifies to 0 minus 1 plus 8, that's 7, over, in the denominator, I have the square root of 0 plus 1 plus 16, that's root 17, times the square root of 36 plus 1 is 37, plus 4 is 41, so the square root of 41. So I'll do inverse cos of this ratio, and I'll get an approximate angle measure. And it's about 74.6 degrees. That's the angle between the vectors if they're placed tail to tail. Example 8 says find a vector that is orthogonal to the vector 3, 4, 5. And I didn't even give this vector a name. Let's call this vector u. So let's find a vector orthogonal to that. Orthogonal, that's a fancy word that means perpendicular. So what do we know about vectors that are perpendicular to each other? Vectors that are perpendicular to each other form a 90-degree angle with each other. And if they have a 90-degree angle, the dot product of them would be 0. So we need to find a vector that when we do the dot product with vector u, we get a result of 0. So how can we do that? There's a couple different ways. So let me make a note. V and u are perpendicular if v dot u equals 0. So let's come up with some vector v that when we do a dot product with vector u, we get 0. So what we can do, we can actually just make up two of the components for vector v, and then solve for the third component, which would make the dot product be 0. So vector v, let's make up a couple components for it. Let me make up the x and y component. How about 1 and 4? And then I can solve for the unknown z component. So now I can set up my equation. Vector v dot vector u has to equal 0. Since vector v dot vector u has to equal 0, I know that vector 1, 4, z dot vector 3, 4, 5 has to equal 0. And how do I do the dot product of two vectors? I multiply the x components, plus multiply the y components, plus multiply the z component, and now I can solve this equation for z. So 16 plus 3 is 19. Move the 19 over, I get 5z equals negative 19. Z equals negative 19 over 5. Therefore, vector v, which was 1, 4, z, so negative 19 over 5, is orthogonal to vector u. Let me prove that to you in GeoGebra as well. Okay, here in GeoGebra I have vector u and vector v drawn, and notice that the angle between them, it's indicated right here with this 90-degree angle symbol. So the angle between those two vectors is in fact 90 degrees. And there's an infinite number of vectors that are perpendicular to vector u. We just found one possible vector that's perpendicular to it. Let me show you a shortcut that would actually be quicker to do. Okay, so same question, same vector, vector 3, 4, 5. Let me just show you a shortcut to coming up with a vector that's perpendicular to it. To come up with a vector that's perpendicular, it needs to be a vector that has a dot product with u to be 0. And I can guarantee the dot product is 0 if I do the following. Make one of the components 0. So how about the first one? It could be any of the three, but I'll make the first component 0. And then just swap the other two components. So instead of 4, 5, make it 5, 4. And then switch the sign of one of those two. So let's make this one negative 5. Let me show you that this is perpendicular to vector u. Okay, so notice here I plotted vector u, and then my new vector, vector 0, negative 5, 4, is over here. Notice they're perpendicular as well. Like I said, there's an infinite number of vectors that are perpendicular to vector u. Let me just show you one more. So like I said, the shortcut is to make one of the components 0, swap the other two and change the sign of one of them. So how about we make the z component 0, and swap the x and y components. So instead of 3, 4, it becomes 4, 3. Make the z component 0, and now I need to switch the sign of one of these vectors. So how about let's make the y component negative, and let's see if that vector w is perpendicular to vector u. Yes, once again, I have found a perpendicular vector indicated by that 90-degree symbol. So hopefully you understand how that shortcut can work. And let me prove to you that doing this method actually guarantees that the dot product is 0. So let's prove the dot product is 0. U dot v would equal 3 times 0 plus 4 times negative 5 plus 5 times 4. And if this dot product is 0, that proves algebraically that they are in fact perpendicular. So I've got 0 minus 20 plus 20. That's 0. So the dot product of those two vectors is 0, so that proves to you that these are in fact perpendicular, so that shortcut does work. Example 9 says find the magnitude of the projection of vector u onto vector v. So let me just give you a visual demonstration of what we're looking for here before we go ahead and use the formula that we figured out earlier in the unit. Okay, so here's vector u, here's vector v, and what we want to do is figure out the magnitude of the projection of u onto v. And if we were to project u onto v, it would be represented by this purple vector here. Tail is at the same place as the tail of u and v. It's parallel to v because we're projecting onto v, and its tip stops at a point, so that if I connect it to the tip of u, it would form a 90-degree angle. So we're looking for the magnitude of that purple vector there, the projection of vector u onto v. So we want the magnitude of that purple vector. And we can find the magnitude of that vector using this formula we figured out earlier in the unit. So the magnitude of the projection of vector u onto vector v would equal the absolute value of u dot v divided by the magnitude of v. So I need the absolute value of this. So u dot v, find the product of the x components, 3 times 5, plus the product of the y components, negative 3 times 2, plus the product of the z components, 2 times 0. Divide this whole thing by the magnitude of vector v, which I could find by doing the square root of the sum of the squares of each of its components. And I need the absolute value of this, but I know this is positive and this is also positive, so I don't need the absolute value symbols. So I have 15 minus 6 plus 0, that's 9. And in the denominator, I have the square root of 25 plus 4, I have root 29. So this is the magnitude of that projection. So in GeoGebra, I got it to calculate the length of that projection vector. It says it's about 1.67, and I just want to show you that that is what the approximate value of 9 over root 29 is equal to as well. So we've correctly found the magnitude of that purple vector, the projection of vector u onto vector v. So that's it for working with vectors in 3 space. The next lesson, we're going to get to learn another product of vectors. Now that we know how to work with vectors in 3 space, we can learn something called the cross product. So make sure you watch that video as well. And make sure to try the practice questions that go along with this section so you get comfortable working with vectors in 3 dimensions. So that's it.